All right, terrific. So we are live on YouTube and here on Zoom. So welcome everybody to the Materials and Manufacturing Seminar. So we have another speaker whom Kubra will introduce in just a moment. So we have some new viewers as well. I welcome a couple of people from the Aerospace department. And thank you for those who've had meetings with her. So Kubra, why don't you go ahead and introduce our speaker and we can get started.
Hello everyone, thank you for joining the seminar session today. It's my pleasure to introduce Professor Tresa Pollock. Professor Pollock received her BS from Purdue University Metallurgical Engineering Department in 1984, and she received her PhD in Material Science and Engineering from MIT in 1989. Then she worked in General Electric aircraft engines from 1989 to 1991, and she worked as a professor in Carnegie Mellon University Material Science and Engineering Department from 1991 to 1999, and she was again a professor in Material Science and Engineering Department at University of Michigan from 2000 to 2010, and she is currently an Alcoa Distinguished Professor of Material Science and Associate Dean of Engineering in University of California, Santa Barbara. Her research interests lie in the mechanical and environmental performance of materials in extreme environments, unique high temperature materials processing paths, alloy design, and 3D materials characterization, ultra-fast laser material interaction. Her work is highly recognized and she has received multiple awards. So a few of them are here listed. She was elected to the US National Academy of Engineering in 2005, and she was also elected to the German Academy of Science, Leopoldina, in 2015. And she is currently a DoD Vannevar Bush Fellow and Fellow of TMS and ASM International. She serves as editor-in-chief in the Metallurgical and Materials Transaction family of journals. And from 2005 to 2006, she was the president of the she was the president of the Minerals, Metals, and Materials Society. So with that, let's welcome Professor Tresa Pollock one more time. We are excited to have her here as our speaker. With that, I'm gonna stop sharing my screen and it's all yours.
Okay, thank you very much, Kubra, for that introduction. And now's the time to see if technology will work. Can you see my screen?
Yes.
Okay, thank you. So thank you very much for the invitation to speak today. It's nice to see some familiar faces that I haven't been able to see in a couple of years, but hopefully soon things will be back to normal. So today I'm going to talk about 3D printing, and that will be with a focus on aerospace materials. But before I start, I'd like to acknowledge a long list of people on the left who are students and postdocs and collaborators in my research group here at Santa Barbara, and collaborators at various other places listed on the right. So I'm sure that everyone has paid attention to some degree to additive manufacturing in the past few years. And there are many benefits to it, potential benefits, with regard to design, development speed up, part reduction, and the ability to print complex things, less machining, lightweighting, manufacturing. And I think importantly, given the environment that we live in now, sustainability. And so there are some very interesting studies on sustainability of additive manufacturing emerging, and the numbers are interesting and rather large from the point of view of cost reduction and potential energy reduction for using these sorts of techniques for producing materials. Obviously, also CO2 emissions go with that. And if you read some of the literature, what seems to be emerging is that these approaches for metallic materials are promising for high value, low volume markets. And certainly aerospace would be one of the places where it could have high payoff. But on the other hand, if you look at the state of 3D printing and where people are producing industrial products, you see that aerospace actually is currently a rather small slice of the total business. And of course, the reason for that is safety related, that when we print things that are going to fly in critical applications, it's absolutely essential that we understand everything about the structure as well as the defects that arise in the printing process. The other challenge with regard to aerospace, as well as other sectors of industry, is this business of the selection of materials available in powder form if we're going to print from powders. And there are something like 5,500 well-known alloys that are used in common industrial applications. But if you go, for example, to the GE webpage and look at the selection of materials available to be purchased in the form of powders, you see a rather short list. So there's cobalt chrome, and this is the alloy that GE has used to make their fuel injectors that are currently in service. One can get titanium, a couple nickel alloys, stainless steel, and aluminum casting alloys. But in fact, the selection is rather limited. And so one of the challenges is to develop alloys that are tailored to this process. Now, as I said a moment ago, what we really must do if we're going to print things for critical applications in aerospace is really control structure to a high degree. And so I show here a print. This is the work of De Hoff and Kirk at Oak Ridge. And they did this very clever study a number of years back now, but their point was to show that they could control the columnar to equiax transition during printing, and in doing that, be able to print DOE into a laser powder bed process. Now you'll see that this is not perfectly well printed. And so the question is, can we really control this structure to an even greater degree? Now I show here an experiment conducted in collaboration with Amy Clark at the Colorado School of Mines. And this is at the Advanced Photon Source, where one can take a small sample and using X-ray imaging, scan a laser beam across the surface. And so you can see individual powder particles here. And in looking at this movie, it's quite obvious that this is a very complicated process to control from the point of view of where physically all the powders are and what goes on in the liquid, and understanding how to control that over very large volumes. And so really what one has to pay a tremendous amount of attention to is what happens in this melt pool at the point where either a laser beam or an electron beam interacts with the material. So today I will focus on both laser powder bed and electron beam melting, and neglect other processes such as wire additive manufacturing, for example. So in both the laser and electron beam processes, you have this melt pool that's maybe a few hundreds of microns in extent, in width and depth. And what are all the things that you have to worry about? Well, there's the nucleation of solid from the liquid phase and the formation of the grain structure. One has to worry about the gradients and velocities at which these interfaces are moving, the degree to which you remelt material below when you scan the beam across, the potential for cracking, residual stresses, lack of fusion, what happens to that powder, and how much of the material is vaporized. And so what we've been trying to do is really understand a lot of these details at the scale of the melt pool. And so this is sort of at the scale of cubic millimeters. Now, to do that, we obviously need to look at the material in 3D. And so I show here a system that we've developed over the last decade or so since I've been at Santa Barbara. And we call this the tri-beam system. And so what this basically is a Thermo Fisher TFS fib microscope. And so that means we have an electron beam and an ion beam. And what we've done is coupled a femtosecond laser with this microscope. So a titanium sapphire laser that operates at 780 nanometers. And this is a femtosecond laser. And I'll explain in a minute why it's important that we use femtosecond lasers for this sort of thing. And so this is what it looks like inside the microscope. So you can see the laser beam coming in here and all the other EBSD and electron columns here. And so the motivation for doing this is to use the femtosecond laser to remove material layer by layer so that we can get 3D data, both chemical and structural, by using these other detectors, EDS, EBSD for crystal structure, and backscatter imaging for structure itself. And so the way that we do this, okay, I think that's all right. So the way that we do this is we take a sample, and with glancing incidence, we just scan the laser beam across. And in scanning the beam across, what we're doing is ablating a liquid-like layer that's about 30 to 50 nanometers in extent. And so this is just an MD simulation that gives you some sense of what that is like. So we basically deposit the radiation. In the short term, nothing but electrons interact with the system. And then in a matter of maybe nanoseconds, a liquid-like layer comes off. And because this whole process takes nanoseconds, by the time this layer is coming off the material, the beam is off. And so what that means is that you're no longer putting energy into this layer. And then what you end up with is a very low damage surface that you can directly image in the microscope. And so I show here a number of different materials after ablation. And what we're showing here is the fact that you can ablate material with very little collateral damage to the material, with the possible exception of very, very soft materials, because when you ablate, you launch a shock wave here. And so in very soft materials like copper, you do inject some dislocations into the surface. There's also a little bit of roughness, and this has to do with the details of the laser material interaction, but these things do not interfere with imaging. The other thing you'll notice is that a lot of different materials can be ablated without any substantial damage. Now I'm stuck. Let's see. Oh, there we go. Sorry about that. So this setup shows the sample in the microscope. And as I said, we go at glancing incidence. And so this is really just an example about workflow. So you can see a sample here that's been 3D printed. And this data set that you're seeing layer by layer here has been collected over 60 hours. There's 25 gigabytes worth of information here. And each slice takes only 25 seconds. So the femtosecond lasers are very effective for speeding up the process of developing a 3D data set. In some cases, we may use the focused ion beam to slightly clean up the surface and knock off some of those periodic structures that I showed you at the surface. And then depending on what kind of information you want in each layer, one must commit varying amounts of time to gathering that data. And so as you can see here, we make a pedestal and then we remove the material layer by layer. And so this particular data set is something like almost 1 millimeter by 1/2 millimeter. For some reason, my computer is not wishing to advance the slides. Okay, so I show here the materials tomography library that we've developed over the past few years. And the point of showing this is to demonstrate that this really is a materials blind approach to making tomographic data sets. So we have everything from superalloys to geological samples to ceramics to composites. And so the reason that it's materials blind is the fact that the ablation process is fairly similar as one goes from material to material. Now, as I said, we're gathering a lot of data here, and it turns out additive manufacturing on many fronts is really a data problem. And so what you can see here is that you gather these different modalities of data, and there are big chunks of data that one stores. And the biggest part of that is the electron backscattered patterns that give you the grain orientations. Now, another challenge with regard to using different sorts of detectors is that they all have different distortions. And so one has to find corrections and approaches to merging the data into these 3D data sets. I'll show you a series of 3D data sets, but I do want to emphasize for those of you who are interested in tomography that there's many phases to getting the data into useful form. And so acquisition's just the first phase. And I've shown you this tri-beam approach. There are, of course, many other approaches like X-ray tomography. And once one gets the raw data, then there's a lot of things that you have to do to bring it together. So in particular, we use a lot of dictionary or spherical harmonics indexing. These techniques have been developed by Mark de Graaf at Carnegie Mellon. We have some machine learning approaches that allow us to bring data sets into the same frame of reference. And then that's not the end of the day. You still have to develop a lot of techniques to actually analyze the data. And so things, for example, that we can get from some of the data sets that we're gathering include geometrically necessary dislocations. So we can have the full tensor because we have a 3D ABSD data set. We can get information about nucleation and use this information to feed it into structure property models. And then there's the whole business of sharing and curating. I'm not going to talk about this much today, but we've been working with computer scientists to develop some approaches to share the data and to operate on the data in the web. And so this is a challenge also for any large data volumes. Now I'm talking about the data that we have at the melt pool scale, and we all know that that's a very small volume compared to the total volume. And so from the point of view of future challenges for additive manufacturing, data is certainly high up on the list. And so if you imagine that you're building a part and basically gathering image information, and that the build is 3 days long, you're likely to generate something like 230 gigabytes of data. And so bringing this sort of data and to the melt pool scale is yet another challenge. And so there are many things for those of you who graduate and work on this in the future to do. So this is an image of software that is open source that we use to reconstruct the images. This is Dream 3D. And so if any of you are interested in trying to work with some 3D data, you can go to this website and there's some sample data sets there. And you can get a feel for what the challenges are in bringing these data sets into 3D imaging. Okay, so let's talk about 3D printing at the melt pool scale. And what I want to show are 3 different experiments and the sort of information that we can get by looking at the structure at the scale of the melt pool. And so what these experiments are electron beam printing of the nickel alloy iron 718. And what we've done is basically printed to steady state. And then on the very last layer, put different sorts of conditions so that we can understand the relationship of the printing conditions to the structure that develops. And so what we have here is a spot melting strategy. And here are the details of the build area. And what we're trying to do here is more or less hold the beam printing conditions constant, but vary something else about the build. And one might assume, and people often do assume, that since you're operating at basically constant conditions, that you should develop the same structure. And instead, what you'll see is that all of these details matter a great deal with regard to structure development. And so in this particular case, you're going to see a data set where we've sectioned a piece from the very last part of the build where we've made a spot melt in this region. Okay, so for those same 3 conditions, I show you 3D data sets here. And the first thing that you'll notice, we're looking at electron backscatter diffraction data. And these are the grain orientations relative to the build direction. And so the first thing you'll notice is that in these 3 different builds that we have a completely different grain structure in spite of these near constant processing conditions. And I'll say a little bit about each one of these data sets and emphasize the things that we can learn from being able to look at these things, at the structure in 3D. Okay, so here is the isolated spot melt. And what you're seeing are slices of the tri-beam data set. And if you look closely here, you can see where the melt pool is because the structure changes as we deposit this spot melt at the top. If looking top down, this is what that region looks like that we just sectioned through. Ooh, yes, okay, sorry. And so I make the point here that we have a raster in the background with the spot melt on top. And so what one can see in this 3D data set is that this raster melt that we use to get to steady state develops a strongly columnar structure. And for applications in aerospace, columnar structures are often desirable because grain boundaries are places where damage can accumulate in the structure. And so we have the strongly columnar structure with this melt pool at the very top of the structure. And what you can see is that there are some grains that have nucleated on the surface, and there are some grains that have actually melted epitaxially and grown up through the melt pool. And so given that we can very clearly define where that melt pool boundary was from the sections, we can now actually separate the entire melt pool from the rest of the structure. And so again, you see that all of the red grains have grown up from beneath due to remelting. And then we have all these grains on the surface which have nucleated independently. And so what this allows us to do, since we have the volume here, is actually count the nucleated grain density. And so in this case, the new grains that have nucleated account for 11% of the volume. Now, why might we want that information? Well, because we want to be able to connect the processing parameters to the structure that develops. And so if you study solidification, you know that the main parameters are the thermal gradients at the interface and the interface velocity. And there are models for how one transitions from that columnar to equiaxed structure. And all of these models require information about the density of nucleated grains and information on the material itself. But the missing information in many of the models that have been applied to additive manufacturing is this nucleation density. And so we are able to, we're able to use that information now to build models to predict structure. And so here I show two maps of velocity and thermal gradient for two different modeling conditions, one which only has heat transfer, one which includes fluid flow. And now that we have all the information, we can track the fractions solid from 0 to 1 through these transitions in structure as we go from fully liquid at fraction solid 0 to the grain nucleation events at the end of the process. And so it is still early days for having models that accurately predict all of these things, but one has to work your way through the problem in terms of gathering all the critical data. Okay, so let me talk about the spot melt square setup. This was the conditions in the middle of the 3 data sets that I showed earlier. And so this particular data set has 610 slices and 2.6 terabytes of information. You can see the dimensions here. And you can see basically this data set has a structure which is much less columnar in the steady state. So this is the steady state structure. And then we've again deposited this spot. Is this blocking everything? Sorry. So
definitely where Waldo was hiding.
Okay, so here now we have this this spot, and you can see that the conditions in the melt pool were completely different. And so again, we want to understand how this structure developed, and so we can track the grains back through the layers. So here is the top of the melt, and here are the grains that extend into the previous layer, into the previous layer, and so forth. And so one can basically track the development of these grains and understand the degree to which we have independent nucleation versus grains that persist from the layers below. And so what you can see is that at this top, in this top layer, there are actually many grains that extend back 10 layers below the melt surface. And so this is one of the things that has to be included in the modeling. One cannot necessarily just on the fly change the structure because there's all this history from the layers below you. Okay, this is the, just another example of things that one can find in 3D associated with the process. And this is one of the real challenges for using these materials in aerospace. So as we section through the material, you can see obviously there's a defect of some sort here. And if you look at the grain structure here, what you'll notice is that these defects seem to be associated with grains that have different orientations from the surrounding material. And so if you take the 3D data set and look at this lack of fusion defect, you can clearly see the size of it here. But what you learn from looking at the 3D data is that, okay, there's some disturbance in the build process, and that results in lack of fusion and a void here, but that defect actually extends well beyond the moment where it was created because it requires grains to renucleate as equiax grains in this background of columnar structure. Here are some other sorts of things that we've been able to learn about the process. If you take the columnar grain data set that I showed and look at the misorientation in 3D. We all know that cracking and residual stresses are a major challenge. And what one can see from the 3D EBSD data is the buildup of tremendously large misorientations. And these are the locations where one might expect a crack to develop eventually. But the important point is that these misorientations are not uniformly distributed in the structure, and that if one tracks individual grains as they solidify, there is some tendency for the misorientation to build up in the regions where we have the final solidification event. And so again, controlling the gradients and velocities strongly influences that. And so just to put in perspective that 10% misorientation, here is a couple of different materials. Here's the 718 that we've been working on. When you get something of the order of 8 to 10 degrees, you might expect a crack to start to develop while printing these materials. Here's another alloy, Marium 247, and you can see that there are cracks that have been developing throughout the build. Now, the challenge here is that Marium 247 is an example of an alloy which has very, very good high temperature properties. And so it would be a very desirable alloy for printing, but it's not really possible to print it without cracking. And so now we come to the question of, well, how are we going to make printable alloys that don't crack, but are strong enough to serve in these aerospace applications? And so a number of my students have been working on this problem in different ways. One approach is to actually work with the powders themselves and try to go through processes where you functionalize the surface of the powders to enhance the nucleation process in the melt pool. And in doing that, you create finer grain structures, which have less tendency for cracking and hot tearing. And so this is quite useful for things like high strength aluminum alloys. On the other side of the house, where you, for example, do not want very fine grained structures. So for example, in high temperature applications, then it becomes necessary to really modify the solidification path by changing alloy composition. And so here's a close-up of the functionalized nanoparticles. If you'd like to read more about this, there's a paper. But in doing this functionalization, one is able to modify the nucleation events as this powder is melted. Okay, so with regard to getting high strength alloys that can be printed with columnar grain structures without cracking, we've been working on a new class of materials, cobalt-based alloys. And I show here the structure of one of the early simple ones. And the motivation for this class of alloys is that they're two-phase. We have an FCC cobalt matrix and an L12 precipitate structure here, and the precipitates provide strengthening at high temperature. These alloys look similar to current nickel-based superalloys, but have somewhat higher melting temperatures and very different properties with regard to solidification. And particularly important is they have a highly tunable solvus for these precipitates, so the temperature at which all the precipitates go into solution. Now, when one solidifies materials at moderate gradients and velocities, you always have a dendritic structure. And the contrast that you see here is due to segregation during solidification. So if you go to the electron microprobe and lay down a fine grid of points and measure composition and plot those compositions based on low to high cobalt, because that's what one would expect for a solidification path, then you can fit to these curves a Scheil analysis for solidification. And the important parameter here is the partition coefficient, which is the ratio of the concentration of the solute in the solid. So in early solidification compared to the concentration of the solute in the liquid. And so for this alloy shown here, and I should say that when the partition coefficient is far from 1, we will obviously have strong segregation to either the dendritic or interdendritic regions. And this can create opportunities for convective instabilities or cracking. And so one would really like to have as little segregation as possible. And so in these cobalt alloys, unlike nickel alloys, which have strong segregation of basically all of the elements in the alloy, here you can see that many of the elements do not segregate very strongly, with the exception of tantalum. And with this comes a much narrower freezing range for these materials. So knowing that, we've sort of assembled a set of tools to design some new alloys that would be printable, but also have the ability to form alumina as a protective layer when one goes to very high temperatures. And so we, with my colleagues here at Santa Barbara, over the past 5, 7, 8 years, developed a set of tools that we can bring together to try to guide the alloy design process. And among these tools are density functional theory, coupled with Anton van der Ven's chasm infrastructure, which basically allows you to do the finite temperature aspects of alloy design. In situ experiments in the SEM, where we can watch dislocation glide and connect that to the fault energies that we calculate by these techniques, thermodynamic databases, our tri-beam system, calculations about coatings, because one usually needs coatings, the solidification aspects, and then finally the oxidation part of the story, which in brief is really a difficult problem because oxides are hard to be predictive about in terms of compositions and use of DFT. And so in this case, we've just taken a combinatorial approach where we vary aluminum, nickel, and cobalt, and then using the Raman, the photostimulated laser spectroscopy, search for rapid alumina formation. So we just oxidize samples for an hour, scan them, and see if we can find the alpha alumina peaks. And so bringing together all of these tools, we sort of went through a few generations of materials and then basically ended up with some alloys that are a near balance between cobalt and nickel. Here's the composition shown at the bottom, and then aluminum for formation of precipitates. And so with the combinatorial experiments, we end up at this final composition that I show at the bottom. You can see when this material is oxidized at 1100 C, there's a layer of alumina here. And we have a high volume fraction of precipitates up to 1200 C. So this means the solvus of the material is at 1200 C. And I show this in comparison to a nickel-based single crystal superalloy. And so what you can see is that these alloys are similar in principle to superalloys that are currently flying in aircraft engines up to about 1100 C, and that they have a lower solvus compared to most nickel alloys. And this becomes very important to the printing process. They also have densities that are similar to existing nickel-based alloys. And here I show some data on creep properties. And so this cobalt nickel alloy demonstrates properties that are similar to first generation single crystal superalloys that currently fly as turbine blades. One of the reasons for assembling all of these tools to try to do calculations on alloy compositions before we make powder is the one of the major challenges of designing alloys for additive, because one must acquire powder. That means that you have a very expensive step in your design process, which it involves atomization of the powder. And so one needs to assemble these tools to the degree possible and do those calculations prior to making the powders. So this is the alloy that I just showed you. And we did procure a batch of powder from Carpenter Technology, and basically separated into size distributions appropriate for printing by electron beams and by laser powder bed. And I show here some preliminary print trials where we're looking at processing conditions and printing bars where we can test properties. And we've also printed some artifacts that look a little bit like turbine blades. And you can see that we've been able to print these without any cracking. And so I think this is the first instance of a material which has this very high volume fraction of strengthening precipitates that is printable both from the perspective of simple objects, but also more complex shapes. Now I show here the structure of the material from the laser versus the electron beam printed material. And so in the case of the electron beam printing, one uses a higher preheat. So we have a tendency for more columnar structure. And earlier I showed you some lack of fusion defects that caused grain nucleation. This is not a lack of fusion defects, but it certainly is a transition from columnar to equiaxed. And so this is not what we would predict. And so we're in the process of making data sets to really understand the details of why this transition happens. And one can see in the lower preheat laser material, a more columnar structure. And so recall the alloy I showed you earlier, Marium 247. This is the one that prints, that cracks very badly as one prints it. And so I'm showing the properties of the nickel cobalt alloy that I just discussed in comparison to that Marium 247 alloy and another similar alloy, IN 738. So these are both nickel-based alloys with high volume fractions of precipitates. And so you can see the blue curves here are the electron beam printed cobalt nickel alloy. And we have, even in as printed form, the dotted line, we have very high ultimate strength and very high tensile ductility. And if one does best effort on printing that 247 alloy, you might get something of the order of 5 or 7% tensile ductility. This is the SLM material. And again, as I said earlier, the SLM process has a lower preheat, and so finer structure and greater tendency for cracking. So here the nickel alloy is 738. You can see that in printed or solution heat treated and aged forms, we have very, very limited ductility. But the cobalt nickel alloy then again has fairly high strength and good ductility. And so our working hypothesis about why we're able to obtain these high ductilities in the as printed conditions really comes back to the fact that we've controlled the solidification path such that we're able to avoid cracking in the liquid state, as well as in the subsequent cooling down through the solvus down to room temperature. Okay, so I think that's 9:45 California time. That means I should be wrapping up. And so just to say a few general words, I think additive manufacturing does hold great promise for complex engineering components of the sort that are needed in aerospace. However, we still have a lot to learn about controlling the process. And if we can't control and predict structure, it's going to be hard to control and predict properties and achieve the same properties every time we print something. We've been working on new metallic materials which match the unique aspects of this process. So the cobalt nickel alloy is an example of that. The powders which are functionalized are a different approach. But all of these things really come down to controlling structure and properties throughout the volume of the material that you're printing. And then finally, all the sensors, diagnostics, characterization are tremendously important, but we have a lot of big data problems, and certainly there are many interesting challenges on this front in the future. And so with that, I'm not sure how we wrap this up or take questions, but I would be happy to take questions. So thank you very much.
Thank you, Professor Powell. It was great, and it was an inspiring talk for all of us. So I don't see any question yet. Please, if you have any questions, raise hand and unmute yourself. Yozu raised hand. Okay, so please go ahead.
Hi, Professor. Thank you for the talk. It's wonderful. I have two questions. The first question is that I saw the solidification partitioning coefficient. I was wondering the table in that slide, the partitioning coefficient, is it calculated from the shell solidification on the top left, or is it measured from the grading of the SEM image?
So it's basically what we do is fit the Scheil equation to these curves. So if you measure the composition at the core of the dendrite, that's the very first solid to freeze.
Yep.
If you measure the composition in the interdendritic region, that's the last solid to freeze. And so we're just basically taking all of this data, ranking it high to low, and then fitting the Scheil equation to it.
Gotcha. Oh, gotcha. Thank you, Professor. And the other question is that for the 3D EBSD texture measurement, what is the largest scale you can your equipment can do? I ask because we have noticed some interesting austenite grain refinement in our 3D printed metal martensite steels. So I was wondering if we can try larger scale, several millimeter scale.
Yeah, so if you see this close up of the instrument, you can here's the stage and here's all the indicators. And so it's really the space available in here that kind of sets what size sample you can put in here. And so in practical terms, in our particular instrument, we're kind of limited to maybe 1.5 by 1.5 millimeters. I didn't say, but this system has now been commercialized by FEI Thermo Fisher, so you can actually buy one of these instruments now. And in the commercial instrument, you can maybe get up to 2.5 millimeter size samples. And so I think the way their stages are set up and their lasers set up is somewhat different. And so if you need data sets larger than that, it really, you have to do them sequentially. The challenge, even with those big 2 by 2 millimeter data sets, really would be just the sheer amount of data that you end up with. Then it'd be very difficult to even process it because you need lots and lots of memory just to physically open the data sets and work on them.
Got it. Thank you.
There is one more question from Brandon McLaughlin. By the way, can you hear me?
Yes.
Okay.
Yeah, I'm here. I was just curious, for this process, does the material flow come from the top or the bottom? Because you're printing something 3D, correct?
Yes.
So does the new material flow in from the top? Do you print it from the top up or the bottom down? I mean, where does the material flow in?
You basically sweep a layer of powder across, take the laser or the electron beam across it, then sweep another layer. So you're building up.
Okay, thanks.
I don't see any new question.
Hello, I just had a quick question.
Mhm.
Thank you for the talk, by the way, it was phenomenal. I did have a question, and you touched on it briefly, but why is there not more of a push for developing alloys specifically for the process that it's being used for, i.e. powder specifically for SLM or wire arc or cold spray, opposed to just trying to qualify existing alloys that are just designed for being, melted and machined, etc.
Yeah, that's a really good question. I think part of it is that, aerospace is very conservative. And so it's much easier to convince someone to do something new if it's not completely new. So if you can take an alloy that's known and print it, there's a little more comfort with taking that risk, I think. And so it's a slow process to adopt new materials into these sorts of applications. But I think, once people become comfortable with the idea that they need to print things or want to print things or that it makes economic sense, then the next step is surely we can do a better job than this. And so, as academics, we get to try out some of those ideas first because it's our job to be looking around for new things. But I think, if printing really sees widespread application in aerospace, that there will be new alloys coming down the pike that are specifically developed for that purpose.
Thank you.
Okay, any more questions for our speaker? All right. Actually, I have one quick one. So you mentioned potential for lower energy use and emissions for additive manufacturing. Wonder if that depends in part on the process that's used or the feedstock, like the powder versus wire. Can you talk about that?
Yes, it does depend on that. And there's a very recent paper. If you're interested, I can send it to you. That really does a more fine scale calculation based on the feedstock character, and I think you see a clear separation between the wire and the powder. And the other thing you see with some of these analyses is it's surprising how much energy goes into machining itself. And so a big part of the savings comes from, you're not machining an ingot, you're not machining the final part. And so machining's very energy intensive. And so if it weren't for that, I think, the trade-off would be much less pronounced.
Makes a lot of sense. Terrific. It's just about 12:55 here now. So I think
Adam, I have one quick question.
Oh, sure. Go ahead.
Tresa, just one quick question, please. Do you see any advantage or research in the direction of creating these alloys with solid state additive?
I'm not as familiar with that area, but I think that's a really interesting process. I would imagine the criteria have a lot more to do with A, plasticity, and B, surface oxidation and things of that sort. That seems to me, I haven't seen any work in that area, but it certainly seems like an area that could use some attention.
Thank you very much. Wonderful talk.
All right, well, thanks again. Let's thank our speaker. And so we really appreciate you coming. And I will end the recording at this point so people can get to class.